I'm David Parks. I'm the Dean of the School of Engineering and Applied Sciences. And it is a super pleasure to introduce my friend and colleague in the past and student way back, Sasha Rush. I wanted to tell you a little bit about Sasha and then a little bit about how I was just a little bit involved in inviting him to be here as well. So Sasha, like I said, is a professor at Cornell, and he also works with Hugging Face, and Hugging Face is now part of Google. They're with Google, but they are maintaining their commitment to open source, democratizing access to large model AIs. Sasha has an AB in computer science from Harvard College, which is when I first got to know him, in part as a teaching fellow in my class 182, which we used to joke was AI under certainty. And if that doesn't seem funny, think about it for a minute. You never reason in a world with certainty, but we were teaching a class where we were pretending that there wasn't any uncertainty in the world. He went on to get his PhD from MIT. He postdoced at Facebook Research and was an assistant professor here in computer science from 2015 to 2019. And in 2017 spring, I got to teach a class with him on machine learning. And I don't know if you remember this, Sasha, but those of you that follow the large language model world, and I didn't know what he meant at the time, but he came to me one morning before class and he said, there's a paper that's just come out and it's changed everything. It's changed the way that my field is going to work. He said this the day that the attention is all you need paper hit the archive. I remember that morning when you came to class and you told me that when we were co-teaching. And this is the paper that went on to become the NeurIPS paper that, is really in a true sense the precursor to everything that's happening today in AI. So I just think that says a lot about Sasha, that he noticed that moment very clearly the morning that it happened. And as I'm sure many of you know, which I imagine is why we have such a large crowd, he has become known for his exposition of these incredibly complex AI artifacts with just beautiful blogs, beautiful demos, ways that we can all come into this seemingly complex, hard to understand world. His research is around language models, including alternate architectures for LLMs, how to scale in open model ways, efficiency of algorithms, hardware, and security of AI systems as well. He's won more awards than I could imagine anybody winning for his work. And he's also an amazing teacher, and again, I'll say a democratizer of access to AI, in particular this large language model part of AI. So along with Francesca Dominici, until quite recently, I was the co-director of the Harvard Data Science Initiative, and we were talking, we're like, okay, we need somebody to talk about what's happening in the large language model world. And I immediately said we should invite Sasha to give the tutorial. And we were really happy that he agreed to do that. And of course, I didn't imagine at that time that I'd be here in my new role to introduce him. So this has all come together so amazingly well. I'm going to sit through a few of these, and we're going to hear large language models in 5 formulas. So it's great to have you here, Sasha.
There are chairs here. We promise we don't bite. We're nice, friendly people there too, so please.
Hey everyone. Today's talk is about large language models. The talk is called Large Language Models in 5 Formulas. As David mentioned, I've been putting a lot of this stuff online and trying to get more in the process of doing that. I put a version of this on YouTube that you can watch there as well. It's about an hour, so the talk today will be about 3 hours. So as you can imagine, there's lots of room for questions and interaction. I think given how wide this topic is and how broadly I'm going to survey it, please ask questions as you go. We can go as deep or high level as people might be interested in. So I want to talk today about large language models. At this point, I've kind of assumed you've heard a lot about these. Large language models are extremely useful, they're extremely expensive, they're extremely important, and extremely maybe scary. There's all sorts of emotions they elicit. And a lot of this goes beyond the kind of technical questions of how they work. This is really the only slide I'm going to show today that actually demonstrates them in practice. I just picked a random hard question, typed it in, and you just consistently get out these incredible answers. I mean, they're so well written, they're so consistent in tone, they have whimsy, they respond to ridiculous situations, they're able to pull up certain kinds of information, they're able to combine information in interesting and pretty wild ways. So I'm a big fan. I use them all the time, trying to get in the habit of really like first asking a large language model before I type in a Google query, before I try to code something. And more I'm finding they just kind of do it for me. So I'm pretty impressed by the technology, but from that point of view, I'm just like probably all of you, in that I'm just like, wow, this is cool. This works really well. So what I want to talk to you about today is how you reason about large language models. How do we think about these as objects of study from a computer science point of view? But I want to be extremely humble about what I can tell you. And the kind of true answer is that we do not even understand small language models. I can make a very, very small 100-parameter language model, and I cannot tell you what or why it works. And I really want you to be cautious of people who sell this to you and say, I know how this works, I understand what's going on inside of it, because these systems are extremely nonlinear. These systems have all sorts of confounding or weird factors to them, and we can't kind of give you a proof that they do something in a particular way. That's not to say we shouldn't try, but for the sake of the tutorial, I wanted to kind of stick with things that I feel like I have a handle on, that we can talk about, that we can get some sort of mathematical intuition for. So here's the structure of the tutorial. We're going to do large language models in 5 formulas. I'm going to talk through 5 areas of large language models that are, I would say, pretty much orthogonal to each other that I think I can give you good intuition for. So the 5 formulas are called Perplexity, Attention, Gem, Chinchilla, and Rasp. And just out of curiosity, I'm maybe like if you could show of hands with number of fingers, how many of these have you seen before? Okay, cool. So I'm seeing a lot of 1s, some 2s, no 5s. That's good. Okay. If there were some 5s, I'd be really worried. I think probably you've seen some of them before. But I'm going to go through each of them individually. We'll do the first 2, take a break, and then talk about the last 3. And I think the reason I find these formulas really useful is that each of them kind of breaks apart one part of language modeling that we can think about and reason about independently of the others. So the first is really going to tell us about generation. We can think about generation kind of independently of neural networks, independently of training data. We can think about it just as a kind of probabilistic system. Next, we'll talk about memory. When we talk about memory, we're going to dive deep into the neural network components. We're going to think about how to actually build this, how you might implement it, what its kind of runtime cost would be on your machine. Next, we'll talk about efficiency. For this section, we'll dive into the actual GPU hardware. We'll get an understanding about why these things really are fast in practice, and we'll go through one important example of how this works. Now, if you're not a coder, don't worry. It'll be pretty high level. If you are a coder, you probably actually haven't coded for GPUs. It's pretty hard. I think there's probably only like, I don't know, dozens of people in the world who do it very well. I'm not one of them, but I'm a big fan. So I appreciate the people who can. Next, we'll talk about scaling. So scaling is less about the low-level parts and more about the executive decisions. So like, why the heck did Mark Zuckerberg buy 600,000 GPUs, right? What is the reason we think that makes sense and why it might work in practice? And then finally, we'll talk about reasoning. This is one of the hardest areas and one of the least understood. We'll talk about that by thinking about some of the mathematical models that tell us not how transformers or large language models actually work, but how they might work. Give us a kind of upper bound on the performance of what they could do for real problems. This is one of my favorite areas, and it's one I'm really passionate about. I think it's a little less mainstream than the rest of the talk. Cool. So, caveat, I'm going to simplify. We're going to think about abstractions. I'm going to leave out a lot of the details. You're not going to leave here and go get a job at OpenAI because they care about the details. But maybe you can be like a manager at OpenAI, so you can get a sense of how it works. So I'm thinking about this like frictionless environment. I think someone used the word like, what was it? Spherical cows. So think of this like physics with spherical cows. So it's the kind of like world we're going to be working in as we begin. Okay, so I'm going to get started. Any questions before I get started about LLMs generally? I'm going to make you guys ask questions at some point. I know it's a little scary in this room. Okay, part one. Let's talk about perplexity. Okay, so for this section, we're going to assume that language is very nice. It's going to behave in a really nice way. The way it works is that there's going to be documents, and the documents have T equals 1,000 word tokens. So that means every document is a New Yorker article with 1,000 tokens long. And our language is very simple. It has 10,000 word types. So that means the dictionary has exactly 10,000 entries, and you're not allowed to make up new words ever. Okay? You can't have weird anything. It just has to be those exact 10,000 words. Okay? And this distinction between tokens and types is one that I think often trips people up at first. So one thing to ask yourself in your head is when I say, like, when I make a statement, ask, am I making a statement about tokens or types? Because we're going to see kind of moving back and forth between those two things. So when I talk about tokens, I'm talking about looking back in a document for like a previous word. When I talk about types, I'm thinking about looking in a dictionary to determine what my next word will be. Okay, let's add some formulas. So language model is very well defined. A lot of people will lie to you and call their thing a language model. They're wrong. I'm right. This is what a language model is. It's a probabilistic model of a document. It gives us the probability of a given series of tokens existing, right? The probability of that document existing in the world. The probability of someone writing that New Yorker article. I'm going to go a little bit through notation, just because I know we have people from different areas, and I think sometimes my notation can be a little confusing. I'm not going to be very explicit about random variables. I'm just going to kind of casually write x1 to xp, kind of implicitly stating that those are random variables. I'll make it clear when they're explicit instantiations of those variables. I'm also going to be pretty sloppy about the parameters, but when it's important, I'm going to use a semicolon to split off the parameters from the probabilistic model. I do that because I don't want to talk about neural networks. Neural networks are messy. They're their own world. When I think about them, I need to like turn off my brain a little bit. And so in this section, we're going to mostly just talk about probability because that's well defined. Okay, so I have the joint probability of these T tokens. Next section, we'll talk about theta, but for now, we're going to ignore it. Okay, so mathematically, we can just apply the chain rule to this joint distribution. We can write this joint as any combination of conditionals we would like, but a natural one to pick is left to right. So here I'm taking the product of each individual probability of words conditioned on all the previous words before it. There's no inherent reason I have to do it that way, but it's convenient and it's a nice thing to model. That choice to split up in that left to right order and then to parameterize explicitly the next word is known as an autoregressive language model. Here, auto means that you're conditioning on yourself, on your previous choices, and regressive refers to the fact that you're regressing or predicting the next thing in that chain. So we're going to parameterize the probability of the next word. Let's make that a little bit more tangible. When I say pxt conditioned on the previous words, what I'm saying is learn a model, theta, that looks at the previous words and produces a distribution over the next word. That object is a little bit big. It consists of 10,000 floating point values consisting of the probability of every word in the dictionary. So it's a prediction problem, but it's a prediction over a very large set of possibilities. And when I talk about that, I'm going to talk about it in terms of this histogram, where we have a probability of each of the words in our dictionary. Cool. Any questions about that so far? So we have a distribution. There are two things we'll do with it. One is we'll use it to assess the probability of a sequence of words. The other thing we'll do is we'll sample from it. Because we're sampling from this joint distribution, we can do that by sampling from each of the individual conditionals one at a time. So when we talk about generating from a language model, we're simply going to sample from px1 to get a concrete sample, x sub 1, feed it back into the model, sample again, and continue forward. This is roughly what ChatGPT does when it generates the output. There are lots of other fancy algorithms that people have thought of, but most of the time it turns out just doing this works totally fine. So those are our kind of two probabilistic machineries. One is to compute the probability of a document. The other is to produce a new document by step-by-step sampling. OK. So I've just kind of spent 10 minutes describing to you something you probably saw in your undergrad class. It's not a new idea. And it's weird that we're like so obsessed with these sorts of models right now. For a while, it felt like an old and kind of dusty idea. And so it's kind of exciting to see it kind of come back. It's kind of like thing that used to be in the first class of any kind of NLP undergrad lecture. And you can go back and read these papers. It's pretty neat. I mean, so I think I was always taught that kind of Shannon came up with this idea. There are these papers from Markov that people actually didn't translate until rather recently that kind of describe building these sorts of models in, I think, roughly like 1917. And it's actually kind of ironic because a lot of the research that came after Shannon was on translating language. And in particular, there was a lot of funding, a lot of it at Harvard actually, on translating from Russian to English around that time. And I think one of the reasons they were trying to translate from Russian to English is they wanted to translate all these old Russian papers that had like developed all this machinery. So kind of like through Shannon, you got a lot of the translation of, or early attempts at translating some of these papers. OK. Now, it's not entirely that we just rebuilt the model Markov built. It's a little more complicated than that. And I want to give you two examples of ways that modern models differ from the models that people were playing with back in the day. So the first is an assumption that we used to make until very recently about language models. And the assumption is that there was a fixed length history. So specifically, an assumption, which is known as the Markov assumption, is that each word only depends on, let's say, just the last word. And that assumption doesn't change our probabilistic model. It just says that these two quantities are roughly the same. The probability of xt conditioned on all the words is roughly the same as just conditioning on the previous word. Now, this is obviously wrong, but it's not as wrong as you might think. There is a lot of information about xt and xt minus 1. And most of the information probably is in the last couple words. So making some sort of cutoff is not too kind of crazy an idea. The second assumption is that people used to assume that theta could be represented by just a kind of good old-fashioned categorical distribution. So what I mean by this is that instead of learning a kind of fancy neural network, we just assume that there was one categorical distribution for every last word. So if I saw the word the, I would just memorize the distribution over next words. If I saw the word dog, I would memorize a different distribution over next words. And the reason that was really nice is because you could estimate those distributions exactly, very efficiently. So you could go over the entire internet, just count up all the times you saw dog, count up all the next words, divide, and you'd get these pretty good language models very efficiently. And so if you think about tools like MapReduce or things like that, always the kind of first example they would give you is how to build this kind of language model, how to count up all the different kind of combinations of words on the web. And this was kind of the primary way people did it up until about 2010. So it's not too crazy an idea either. Okay, so what happens when you do this? So you get something like this. So this is a sample from the language model I've described so far, from Shannon's paper in 1948. I always think this paper is so cool. It's so cool that he just sits down and builds a language model, I guess by hand or something, I don't know. And so he gets something that I don't know, it's really bad, but it gets kind of roughly the order of part of speech tags of words in English, the seems to come before nouns. I mean, there's a lot of kind of structure here that, I don't know, impresses me for 1948, even though it's mostly nonsense. Cool. So yeah, so if you go read this paper, he does this for a bunch of different models, a bunch of different tasks. Cool. Stop for any questions. So this is bad, but how do we know it's bad? How do we quantify that one language model is better than another language model? How do we quantify this idea that it's capturing something about English, but not getting English exactly? And we're going to do this the same way we would do it for kind of any machine learning model. We're going to have a kind of held out test set. We're going to give it to the language model, and then we're going to compute a metric. But one thing that's a little tricky about this is that this problem, it's kind of unsupervised. We don't have a kind of right answer. We're kind of just trying to learn the distributional properties, estimate the kind of density of language. And so kind of the simple methods might not work as well as you would think. So let's look at an example. So this is going to be the main sentence we'll look at throughout the talk. The dog walked to the blank. Yeah, it's not the most creative sentence, but we'll use it as we go. So we're going to assume that we give this to a language model, and we ask it to produce a distribution or a histogram over the vocabulary. And here's our distribution. And the mode of this distribution is the word park. So that's in some sense our prediction of the next word. But the true answer is lawn. So we got it wrong. So if we were just kind of assessing accuracy, we would say we got 0 points, right? But we kind of did a little bit better than that. We gave some probability to lawn. It was in our top probably 20 words. So we kind of captured the possibility of next words reasonably well. So it's unfair that we got a 0. So we want to get some points for getting lawn, even though we didn't get it right exactly. And what's particularly challenging about this is that certain word predictions are much easier than other word predictions. So there are some cases where it's extremely clear what the next word will be, and there are some times when it's really, really hard. And this example comes up a lot if, say, let's say something like a preposition after a verb. That's pretty easy. Like some verbs can only be followed by one preposition. But let's say the last word was the, and the next word could be like a person's name. Well, there's like hundreds of people's names, right? How could you possibly ever get that right? And what's particularly hard about this is that language has this kind of nasty distribution to it, which is that some words that are super common are very, very, very likely to appear. But other words are much, much less likely to appear. Yet, if you kind of sum up the whole tail of this distribution, it's a non-trivial probability. So like all the time in most New Yorker articles, you're going to see a word that you don't know or haven't seen before, right? That's like a pretty common experience, even though most of the words in every article are super duper common. And so if we just did accuracy, we get a pretty skewed sense of how well we're doing or what we're getting right. Okay, so we need another metric. Oh yeah, go for it.
Can you make a relationship between statistical prediction and semantics?
Yeah, it's a great question. These models that we're looking at now, that only look at the previous word or so, are much more capturing the syntactic flow of language. So they're mostly like, is this type of word reasonable in the next spot? You'll get some semantics just through kind of correlations of maybe like verb and preposition or verb and direct object. But primarily, we're trying to get the kind of structural properties. And that's because that's where kind of most of the information is. This method we're using now underlies all modern large language models. And they clearly capture semantics in a very deep way. And so like at that scale, certain semantic properties show up very clearly in these models. But drawing the line of when you kind of move from just structural information to kind of the semantics or meaning of the language is hard to kind of piece out. Yeah.
Thank you.
Yeah.
You draw the distinction between Markovian and language models, but when you said it's not categorical, maybe my question is ill-posed, but is it like an infinite state sort of system? Because when I think about the Markovian system, it's finite state. You have transition probabilities, everything.
Yep.
And then when it's finite, it's discrete. You can probably find a discrete map.
So really good question. Let's just make it clear what my notation is, because I'm being a little idiosyncratic for simplicity. I'm making two orthogonal assumptions. One is the assumption that the probability distribution is Markovian. So what that's saying is that I can ignore previous words because the distribution is independent of them. The second assumption, which I'm calling categorical, and maybe that's not the right word for it, is an assumption about theta. It's an assumption that we have always just stored internally one distribution for every conditional state. And we're going to kind of relax both of those assumptions in the next section. But for now, does that distinction, is that clear?
It resolves some of the...
Okay. But we'll get back to your question in the next section. Yeah. Cool. Great. Well, I love that you guys stopped me on the zip slide, because it's my favorite as an NLP person. Any other questions while we're here? Okay. So we need another metric for this problem. We're going to choose a metric that also relates very highly to Shannon. The metric is going to connect the fact that we have a probability distribution to the fact that that probability distribution implicitly implies a way to compress language. And the way this works is that we're going to pick a binary string to represent every word in our dictionary. This will give us a variable length code to encode every one of the words in that dictionary. If it's helpful, you can think of this as like a Huffman code. We're basically going to like build a tree and kind of get binary strings for each of them. If that's not helpful, just ignore it and pretend we're like a gambler. We have to distribute these codes to our words. If we pick shorter codes for some words, that implies we have to pick much longer codes for other words because we've kind of used up that space. That assignment will give us a code for every one of the words. And the way we're going to think about this problem is that we get scored based on how short the code was for the red word. So in this case here, the word was lawn, and we gave it the code 100101. So pretty good. It took 6 bits. It would have been better if it had been park. We had a very short code for that, 101. But it would have been devastatingly bad if it was this one below, right? Because we had an extremely long code. We'd basically like use all these bits telling you about this super weird word that showed up. So this is a way we can take our language model, make it into a way to compress language with the assumption that the person on the other end has our language model as well, and they can read our codes. So with a language model and this setting, I can pass the next word in 6 bits to another person. Okay. So whatever this bit is bounded by this formula. It's bounded by log base 2 of the probability we assign to the true next word. So we gave that word, 0.4. We couldn't do any better than negative log base 2 of 0.4. Kind of tells us the code length of that setting. Also comes from Shannon and gives us a way to kind of know, in the best case, how good we could compress that output. So you can think about this as just using our probability distribution to bet on codes for each word. We get rewarded based on how short those codes are. We don't actually have to produce the codes because we have a formula for it. The formula is pretty simple. We just take the probability we gave to the actual true next word and take log base 2 of it. So if the probability was really low, that log base 2 would be really big. If the probability was really high, it could go very small. So for historical reasons, in language modeling, we use a metric that's a slight transform of that idea. It's called perplexity, and you'll start to see it everywhere if you read language modeling papers. It corresponds to 2 to that quantity. So we go 2 to the average number of bits per next word of the system. And what's nice about this is that you can read a complex paper, get to the perplexity, and you'll say, oh, this language model corresponded to like an ability to compress language to this level. You can kind of directly convert those terms, and you can think about what that means in practice. So let's look at some examples, just because I think it's helpful to see these in practice. So if you get down to perplexity 1, you have won. You won language modeling. You're great. It's done. You solved language. Okay. What that means is it implies that the problem and the underlying system was effectively deterministic. You need 0 bits to communicate to the person you're playing this game with, because they can literally just read off what the language model tells them, and they'll know that that is the next word. This feels impossible, but sometimes you'll actually see things like this, where you get to perplexity 1. And the reason is because sometimes you'll do language modeling conditioned on some side information. So for example, like let's say you're let's say you're translating from a French sentence to an English sentence. If you condition on the French sentence, sometimes there'll only be one valid English translation, right? So like if every, say, speaker agrees that this is the next English word always, right, then the perplexity of that part of the language model will be 1, right? There's only one possibility. Maybe you know what it is, and you generate. Okay. If the perplexity is 10,000, that implies that your code is essentially uniform. You're not using the variable length property of language models at all. You're just assigning literally the same code to every word. So that means you're maybe ignoring the fact that there's any structure to the problem at all. You're ignoring that language is Zipfian. You're ignoring any kind of Markov assumption. You're just giving every word the same probability. That leads to all the codes being the same length, and that length corresponds to a perplexity of 10,000. And then just to make it clear, perplexity can be worse than that. So let's say you just really, 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 really think the next word is pizza, and the next word is, I don't know, like business suit. You've like screwed up in a really bad way, right? And so language models will tend to be kind of not so confident, right? Because they never want this bad scenario where you've given a basically infinitely long code to the true next word. That can really hurt your perplexity. And it probably means you have a bug, right? Like if you're coding this up and you see these giant perplexities, you might have a bug. Cool. Any questions about this slide? Yeah.
I think I'm missing something. Is the perplexity evaluated against an actual distribution of language, or is it inherent to the model? Like you said, perplexity of 10,000 is uniform, but you're also talking about sort of your model getting it wrong.
It's a great question. So you need two things to evaluate perplexity. You need a model, and you need a held-out test set. So the most famous one is just articles in the Wall Street Journal. So that's the test set that's held out. And then you're evaluating a model's perplexity on that data. So the test set tells you what the true next word is, and the model tells you what the code for that word is.
And which is just the log of the probability.
That's right. But it's a log of the probability from the model.
The model's prediction probability.
Yeah, that's right.
So then aren't there lots of models that would give you a perplexity of 10,000, not just uniform? Like, is it, you said if the perplexity is 10,000, it's uniform. Is that necessarily true?
It's not necessarily true. Maybe what I meant to say more was it's equivalent to uniform in that, like, it'll get the right answer roughly 1 out of 10,000 times.
So it'll perform as well as the uniform.
I think that's a good way of thinking about it, yeah. Any other questions? Yeah.
So do we expect to generate exactly the article to get, you know, I mean, like sometimes we can generate something different, but still it's really good and impressive, but it's not like word by word the same as the article.
So just to be clear, this metric is not a metric of generation quality. It's a metric of distributional match. So what it's trying to do is it's trying to produce these codes that will match relatively closely to what we see from real language. Now, it just so happens that if you do this right, almost certainly you'll do what you described right. But the converse is often not true. So for instance, let me give you an example. I have a model, and it always outputs, I don't know, David Remnick's New Yorker article, and nothing else. It always does that, right? That model will have terrible perplexity, but its generation quality is really good. It generated a really good article, right? So, like, I think what we're trying to do in language models is slightly more than just generation. It's kind of capturing the structure of language. Yeah?
bit confused. So when you define perplexity, it's is it over all of the token space with like some sort of like?
Great question.
That it's,
So this thing here is over the tokens that you have in your test set. So it's a sum over each of the words in the article. And then this here is the actual observed word at that point.
test.
Test, yes. So yeah, you can think about this as an expectation over language, over like observed language. If you want to be formal, this is just like Monte Carlo over language. We don't have that distribution, so we just have to use samples. Yeah.
So to be really pedantic, given your initial notation, each article in your test set would have a perplexity score, and then your overall perplexity would be averaging those across all of them.
It gets complicated because articles are different lengths, so you can't do it that way. So think about it more like we can cat all the articles in the world to one super article, and then.
But you conveniently said that all articles have 1,001.
Yeah, that's true. In my case, they're equivalent, but in general, they would not be. Yes. Cool. Yeah.
So, because we know the language is not deterministic, so I wonder, let's assume your handout set and training set are from the same distribution.
Yep.
Is there any bounds on what perplexity could be?
Great question. So Shannon figured this stuff all out very early. He has a paper on estimating what's called the true perplexity of English. So he's interested in what the best possible perplexity you could get would be, given that English is not as deterministic. It's going to differ per different domains, but there's a kind of way you can go about doing this. One thing that's interesting is that humans are really bad at this. So you can't just ask a human to give a distribution over the next word. It's really hard. Like if you ever tried estimating distributions, I'm awful at it. So you have to kind of come up with all these tricks to try to get some sort of importance sample estimate of what their true probabilities are. Anyway, it gets very messy. More practically though, this is kind of the history of this data set. This is called the Wall Street Journal data set. It consists of a bunch of Wall Street Journal articles, and then you need to do perplexity on articles you haven't seen. As I mentioned before, if you're uniform, you get around 10,000. Bigrams gets around 600. Trigrams gets around 200. And then 40 years of really, really impressive tricks with 5-gram models gets you to about 140. This is where Google was at around, I guess, 2009, I want to say. They were kind of building these massive, massive models that were kind of 5-gram models of the entire internet, and you get to about 140 on Perplexity. In around, I guess in the 2000s, 2010s, people were building these Markov neural networks that got similar scores. Some of the early non-Markov neural networks got around 100, and things kind of got better from there. I want to kind of give you a high-level sense of why we care. So one person asked about quality. So the question first is, does perplexity correspond to quality? And I mean, you could probably show that it would be hard for it not to, but I can't think of any inherent reason why you couldn't have a model that had pretty good perplexity but led to kind of bad quality generations. Maybe if it was just much too conservative. But in practice, we find that it almost always does. So this is from a paper around 2017. It's showing 2 columns. One is perplexity. If you ever see PPL, that means perplexity. It's in every LLM paper. And then it shows this other column, which is called blue. And this is the metric of quality for translation accuracy. So in this model, it's a language model that conditions on a French sentence and tries to produce an English sentence. The perplexity of the English sentence is here, and the quality of the translation is here. And generally, it correlates almost perfectly with perplexity. So around this time, a lot of people were like, well, if perplexity is all that matters, why don't we just focus on perplexity? It seems simpler. Why do we even focus on sampling at all? Then the next year, another paper came out, and it showed this really surprising idea, which is that perplexity on general language correlates extremely well with task accuracy on totally different things. So this was like a really shocking result and a really cool table. So this showed that you could just take a model, make the perplexity go real down, and then take it and apply it to something totally different. So this is like general English Wikipedia perplexity, and this is movie reviewing. And it's like, why are those things even the same? Like in this paper, at least they were training on translation and testing on translation. This paper, they're like training on translation and testing on like question answering, like totally different underlying tasks. And the correlation is almost exact. So this was really exciting. I thought this was like the most important paper that like I would see published in my lifetime. It basically was like all of NLP up until that point in a single result. And then basically the last 5 years has just been like this result to the moon. So this is a graph from a paper that came out last year called Llama 2. From my perspective, they didn't even need to write a paper. They could just put this graph online. Like I get the idea. The graph shows perplexity, really low numbers here, like stupidly low numbers here, and then like billions of dollars here, right? And it's just like, oh, billions of dollars, it goes down, right? And like it's great. I mean, it's really helpful. I know exactly where they're at. They're at almost knowing language, right? And they, I don't know, spent billions of dollars. Great. I don't have that, but I like the graph. This one's probably only hundreds of millions of dollars. But that's way worse. It's like, I don't know, 0.3 perplexity worse. But this one's really good. So that's great. So now I know the story. Now I know what's going on. Okay. So here's where we're at on the Wall Street Journal. Actually, give me 1 second, then I'll stop for questions. So GPT-3, we think is at 20.5 on the Wall Street Journal. So that's pretty impressive. I don't know what the true perplexity is, but it's capturing a lot of what's going on. It's roughly like, yeah. I mean, I think maybe this is a bad way of thinking about it. There's a lot of words in a newspaper article that no one would be able to predict, right? So most of the time it's probably getting the word right, and then some of the time there's maybe 100 possible choices it could look for. Cool. Now, this is all good, but I haven't actually even told you the punchline yet. I've just told you well, I guess I told you the punchline, but not the joke. We saw Shannon models, we saw the evaluation, but we haven't shown you how to actually make these models that good. So you can guess where we're going. We have to remove these assumptions. We have to move from categorical to neural networks, and we have to consider all previous words. But let me stop here for questions before we do the next formula. Yeah?
You started the lecture, your comments said something about we can't prove anything. That is, we don't understand exactly how it works. We've now spent quite a bit of time creating metrics to evaluate accuracy, quality, and other things. So could you compare our inability to understand it with genuine metrics that we can apparently believe measure the quality or some kind of value of the output?
I think the point I wanted to make is that I cannot prove to you that perplexity will continue to correlate with amazing behavior of language models. That there's no inherent reason why making perplexity goes down makes math ability go up or trustworthiness go up. That part I don't have a kind of step for. What I can say is that perplexity is very well understood and correlates to compression, and that so far we've observed a remarkable correlation between perplexity and human-like ability. So I think if you accept that second one as an axiom, then you're fine. But sometimes people hear that and they're like, I don't believe that. And I don't have any proof of it. Yeah.
So the perplexity that you show in Llama 2, Llama 2 dataset.
Yeah.
Is it over like all sorts of like tokens, or it's just like a benchmark? So is it like an average perplexity across many tasks?
Yeah, I'm being a little tricky here. So you'll note that this says train Perplexity, which is a little sketchy, right? Because like you normally want test Perplexity, not train Perplexity. The reason this is okay is very weird. The reason is because they're only doing a single epoch. So they never see the same data twice. So they can just keep this train value and kind of run it as they go. So it's a little bit in the weeds. I didn't want to get into that too much. But you can think about this as just roughly the internet. And let me give you an example why. Do you see this axis here? This is 2,000 billion, right? So you can think about this graph as just being all of language. You don't need to like be specific because this is everything, right? Yeah.
Because I immediately think about like the tools that I've used for my daily tasks.
Yeah.
Perform better than other in certain tasks because they're designed to do it.
Yeah.
So if just by averaging, so average is just a moment, first moment. So why aren't we looking at, I don't know, second moment, third moment?
I'll give you the same answer I gave him. There's no inherent reason, but so far it's held up. Yeah, in the back.
Is there any reason the interpretation of Perplexity would change if we were modeling not the English language, but a different language or computer language or anything else we could model to predict? Would Perplexity change or would the interpretation stay the same?
The interpretation of Perplexity is the same, but you'll get vastly different scales. So modeling programming language, the Perplexity is much, much lower. There's actually a lot of stuff that's very predictable in programming languages. What you can do as well is compare across different types of models. So let's say you have a model of English words and a model of English characters. You can actually compare their perplexities directly because they're both, in some sense, a joint distribution over the text itself. Multimodal gets a little more complex. You have to have some assumption on like how often you see different languages, and like how you mix them in that way. Cool. Okay. Yeah, one more question, then we'll move to part 2. Yeah.
Okay. I have 2 questions. The first one is trying to learn if this is very applicable to encryption and decryption in cryptology.
Uh-huh.
The second question is if you use a lot of computing software, do you use quantum computing like system to like help you get to like a close prediction?
Yeah, they're a good question. So first off, I think both the language of cryptography and the language of LLM kind of derive from this kind of information theoretic perspective. So I think some of the terminology will be similar. I think a lot more of what we do is data-driven as opposed to kind of constructing a system. So we're much more interested in observing what the information content of real language is versus constructing a system that's uncrackable in certain ways. The second question is interesting as well. Almost no quantum stuff has kind of touched any of this yet. We will see, though, in a later section how much GPUs have influenced these kind of systems. Okay, great. Okay, let's go into part 2. So part 2 is about memory. So in particular, we're going to talk about attention and how attention allows us to relax the assumptions from the first part of the talk. Okay. So first off, let's think about a Markov model that takes into account the previous 2 word tokens and produces a distribution over the next word token. And now, instead of focusing on the probability model, we're going to focus on the parameterization. So we can choose any theta we want as long as the theta produces a probability distribution over 10,000 words. Here's what we're going to use for that distribution. So we're going to use what's called a neural net language model. It consists of 2 parts. The first part is a neural network over the previous 2 words, and then a softmax function. We're going to replace our kind of memorized tables with this instead. Here's the first part. I like this diagram because it conveys how straightforward it is. We're going to feed the 2 previous words, xt minus 2 and xt minus 1, into a neural network. And then we're going to produce something out. Now, the biggest recommendation I can give you when you think about neural networks is to think about the shapes of all the objects. If you understand what the shapes are, then most of the time you can understand how they work. So I have to be a little bit more clear about the shapes. I need to somehow encode xt minus 2 and xt minus 1, and then I need to tell you what the shape of the output is. So the shape of the output is pretty straightforward. It's going to be a vector of length 10,000, because we need a score for every next word. For simplicity, let's do the same for the input. xt minus 2 and xt minus 1 are vectors of length 10,000. And they're all zeros except for a 1 in the position of the index of that word in the dictionary. Okay? So that's all this neural network is. So now we need the size of the neural network, input and output. So the neural network has to take in something that's 2 times 10,000, so 20,000. And it has to output something that's size 10,000, right? Other than that, we can do whatever we want. The neural network can be just a boring old neural network you learned about in your neural network class. There's nothing special here about language, as long as you eat the 20,000 dimensions in and then output the 10,000 dimensions out. Both of those numbers are pretty big, so you probably want your neural network to kind of like make them smaller and then make them bigger again. That's fine, but you can just put together the blocks in that way. Okay? Additionally, we need to train this model. And to train the model, we need a function that maps from a vector of length 10,000 to a distribution of length 10,000. And we need that function to be well behaved. The kind of universal function people use for this is called softmax. It corresponds to exponentiating each of the scores and then normalizing. Okay, so 2 steps, exponentiate each one, and then normalize. So we get a distribution, sums to 1, use it in this way. We just train it, standard way you train neural networks, and you learn the underlying distributions. Okay? So this was like a major breakthrough even when it came out. There are lots of these neural network language models. A lot of them are really good. I think the one that people most remember is one called Word2Vec. Word2Vec came out almost exactly 10 years ago. It won the NeurIPS Test of Time Award this year for 10 years. And what they did is they demonstrated one of these Markov neural networks at a very large scale. So to do that, they had to kind of train this kind of big neural network at a very large scale on lots of data. They had to calculate the softmax 1 million times for every word, and then they learned these parameters and they learned those predictions. They got a pretty good perplexity and demonstrated that this idea could work. Okay. So that's pretty neat. It showed that neural networks could be really good at language modeling. And I think the first thing people thought was like, let's just make these models bigger. If we train this on more data with a bigger model, we can learn more about language, and the approach will get better. But the problem is that this alone doesn't get you there. And you guys kind of know the reason already, which is that this model, even if it's really powerful, can only look at the last couple words. And so it can only reduce the bits of perplexity a certain amount, and it can only take advantage of the ones found in nearby tokens. And once this starts working really well, you start needing to look further away to make some of the harder distinctions. To get from 3 bits to 2 bits, you suddenly start needing to consider kind of wide-ranging semantics of the language. Cool? Okay, so let's just go through an example quickly, just because I think it'll be useful in the future. Let's say we have a model that looks at the previous 2 words. Dog walked, and you have to predict the next one. This one I don't think is necessary. I don't think there's any bits in this word. Walked to, well, it would be pretty helpful to know that it was a dog. So the fact that it's a dog might tell us something about where we're going. Not that much, though. I mean, probably this is going to be a place. I don't know if like dogs walk to very different places than humans, but maybe the semantics of where dogs walk will help us in that prediction. This last one, though, it seems really helpful. We don't know the verb anymore. So we don't know that it's like a location. It could be a person. It could be a country or something, right? So like we've really lost a lot of information here. So in order to like distinguish some of the harder things, we would really like to look back on previous words. Cool. So David Park's example. So imagine in our New Yorker article, it says, we spoke with David Parks in CS. And then, I don't know, 15 pages later, it's a long article, there's some quote and it says, blah, 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 we looked into that, said Professor blank, right? So if you do not know the history of the article, this could be basically any name. Like say there's like, I don't know, 100,000 possible last names. Sorry, I should pick a lower number. 5,000 possible last names, right? And so without any additional information, you're basically going to get that wrong. But if you could somehow remember this and pull it all the way up here, that would be really nice. You could reduce the amount of bits a lot just by having long-term memory. So people had observed this for many years. The kind of building models that could do this kind of thing consistently without kind of heuristics or hacks was considered a really hard problem. Any questions about this example? I think this is an important one we'll come back to a lot. Okay, so what we'd like to do is we'd like to build a model that's fully autoregressive that uses all the previous tokens, arbitrarily far away. Yeah?
So, good question.
Oh, yeah, go for it.
Before. Yeah, so does that mean that you have to know what the document is? Like where the document starts, or maybe it's a chapter of the correction in the book, or, right? Because it could be the previous words, like where does it stop?
Yeah, let's ignore that for now. Let's just assume we've given it documents. The short answer is that all this stuff is going to be a bit stochastic. So like real examples are a bit more complex than this. And so you kind of want it to work pretty well even in kind of harder cases. So you might use context clues like headers or breaks or things of that form. Yeah. Cool. Great. I see some people in the back. There are some seats up here if you are looking for a spot. Cool. Okay, so we want to use all the previous tokens. And a lot of models were trying this. A lot of them go pretty far back. I mean, there are examples of models like this from the 80s, probably even before that. But if we could do this really well, then we could reduce the perplexity even further. And I want to convey a little bit why this problem is non-trivial. So let's look at this example here. So here we want to give the words x1 through xt minus 1 into a neural network and use it to predict the next word. So let's think a little bit about shapes. So the output shape is the same here, right? But the input shape, it's now like pretty weird, right? It could be variable length. Maybe we pick a kind of max input shape. Let's say we never go more than 100 words back, right? But now we have to feed in something that's 100 times 10,000, right, into this network. And that's a little weird. It's like a big thing to take into a neural network. The other problem is if you've seen kind of the arguments that people make for why you need things like convolutional neural networks for images, you kind of have the same problem here, which is that you're asking the neural network to memorize like what position 7 means. And position 7, it's not like a meaningful concept on its own in language. Like the word that just happened to appear in position 7, that doesn't mean anything, right? It's all relative to the other words. You want a kind of model that's able to take into account the fact that language is kind of variable shaped and words move around pretty easily. You don't want to like hard code into your neural network structure the absolute position. Kind of a hand-wavy argument, but hopefully that gives you a sense of why we need something more complicated. Okay, So what we're going to do instead is a method known as attention. You should think of attention as being like random access memory, or like a lookup table or a dictionary in your favorite programming language. The way it's going to work is it's going to save previous information from every previous position, and it's going to let us look up that information and bring it into our nearby context. So let's go back to our dog example. If I say the dog walked to the blank, I have what's called a query, which represents what I know about the sentence at the end. That's going to be in yellow. And we've saved a lookup table for every previous position. So for the, and then the dog, and then the dog walked, and then the dog walked too, we save two values. One value is called a key, and the other value is called a query. We use those to perform the following operation. We can use our query to look up something in our table, pull out the value for that something, and then utilize that green thing to predict our next word. So let's go through those steps one more time. Query looks up key. Key gives you value. Value is used for your prediction. So this lets us take advantage of the fact that we know that it was a dog in order to use that to help us predict the word park. So 3 steps. Query matches key. Best match is picked. And we return the value of that key. So this is pretty cool. It looks like how you'd implement it in code. It lets us look arbitrarily far back in history. It lets us find words that we might need to use. You can see how it might use the word professor to look up the name of that professor and then use it to predict the next word. That's great. There's one problem. The problem is this second operation. So the second thing says argmax is selected. Now, within neural networks, in argmax or like an if statement or any kind of hard selection like this is actually kind of fatal. If you ever have something where it jumps like this and stays, you can no longer learn in that neural network. And the way to think about this is like, imagine the second best guy is here, and then its value goes higher, and it becomes the first best, it goes here, right? So you have this kind of functional form that has a derivative 0, so you can no longer learn with it in practice. So we need another method for going about this problem. And if you've ever seen neural networks before, you know where I'm going. We need to take this function. We need to make it smooth. We need to make it so that it has a meaningful derivative at every location so that we can train with it. Luckily, we have a function like that. We just introduced it. It's called softmax. Softmax is a way to softly decide which was the best choice. It looks like that nice smooth function. And it gives us a way to pick which key we think is the best, while also maintaining a way that we can use it in a neural network. Now, I just want to be clear. This softmax is slightly different than the one we saw before. It's mathematically equivalent. But before, we were doing a softmax over the dictionary. Here, we're doing a softmax over memory. So the softmax is over all the previous memory locations, and it's going to give us a distribution over which ones we want to pick. So let's go through an example of how that works. So we're going to instead do this new thing. The query is going to score the key. The softmax is going to normalize those scores. And then instead of just predicting one value, we're going to do a weighted average of the value. So here's the picture. The dog walked to the blank, query, key, value. The query scores the keys, and we do a softmax over those scores. That gives us a distribution over previous locations. And instead of just predicting a single value, we're going to do a weighted average over the values where the weights come from that histogram. Once we have that value, we can then use that to predict our next word. Now, in the extreme case, where dog was so much better than everyone else, the histogram would put almost all the probability on dog, and we get something that looked like our first method, right? That's why we call it softmax, because it's like an approximation of that full original argmax that we produce. Okay, I think sometimes this can be hard the first time you've seen it. So if anyone has any questions, I'll pause here for a second. Yeah?
I guess I'm unclear on like what the query is that scores the keys in the first place, and what does that query look like? How is it determining?
Yeah, really good question. Let's say, just for simplicity, just to start with, the query comes from a Markov model that just sees the word the. So just like a very simple neural network over only the previous last word. Just to start with. So it's the word the, it knows it needs to predict the next word. It's like, which of the previous words is going to help me in this scenario? Oh, yeah.
Do you need us to
Are you allowed to ask questions? Sorry.
Do you want us to think about the value associated with, say, dog as representing dog or as representing something else?
I think it's fine if you just think of it representing dog.
And then we can think about that as conditioning the neural network for the prediction.
That's right. The reason I'm being a little sloppy with these answers, the kind of true answer is that we're going to run this process multiple times. So the first time we start with just the word, and then the output of this kind of becomes a query, and we do it again. So you get a chance to look at multiple things throughout this process. But the first time, these are just simple. They're just the words themselves. But it builds up more information over time. Yeah?
As you move forward across a sentence, you scan, this memory gets updated, and is that how it works?
Think about it as like you just get a new memory. So none of the memories ever get updated. It's just that as you go through the sentence, this memory table gets longer. But the memories never look forward in time. They only look backward in time. Yeah?
Did you consider the context window to be the same as this idea of memory, or is there a distinction?
For now, we're assuming context window is infinite. So you're seeing the whole article. In practice, context window would consist of a kind of cap on how long the memory could be. So if you hit a fixed cutoff, you start throwing away your early memories. But that's more of an implementation detail. I think in practice, people think we'll eventually get these things to just remember everything. Yeah.
Can I ask, so I can understand why this kind of model, why we still see like logic deduction problems. So I saw a paper that was like, Mary is Tom Cruise's mother.
Yeah.
And the question is, who is Tom Cruise's mother? And we cannot produce a result.
Okay, it's a really good question. Let's do it. If you can stick around, section 5 is going to cover this a little bit more. You have a bit to go. But yeah. But yeah, it's a really good question. We can talk about that paper more. Yeah.
I have 2 questions. So first is that, so what does the key, value, and query means in the semantic perspective?
Yeah.
Second question is why is this sort of the model structure using key and value and query, and its performance a bit better than say word to vec model?
Good question. Okay. Let's do your first one, and then I'll go on your second one. The first question is, what does key, value, and query mean? So let me give you a kind of blunt answer. The blunt answer is the following. Because we did this, we don't have to answer that. So the argument is that if you can make it differentiable and then learn it in PyTorch, you don't have to think about what it means. So we set this up such that it was a mathematical operation that was differentiable. That means we can train it on real data, which means the system can do whatever it wants with it.
So it's just like convenience for objective function.
just convenience for objective function. Like if you can make it differentiable, you can learn it, and then it can learn whatever keys and queries it wants to be interesting. Okay. Let me answer your second question, which is actually where we're going now, which is why, let's see. Okay. Yeah, okay. Well, I'll get there in a couple of slides. Okay, this idea, it was actually an older idea that had been used in lots of papers, but it got really popularized by this paper called Attention is All You Need in 2017. This is like the central paper in language modeling. I highly, highly recommend everyone read and study this paper. I personally basically spent an entire summer trying to re-implement it and wrote up my findings of how challenging it was, but eventually did get there. It basically demonstrates not this idea for the first time, but that this idea was the kind of core idea. So it showed that multiple uses of this attention idea, basically what I've shown you in the previous slide, could basically, they were interested in machine translation, but it turned out the same idea worked in language modeling, but basically just worked really, really well. And it really demonstrated that you could get this kind of holy grail of long-term, full context language model. The model they produced is called a transformer, and this answers some of the questions people were asking. So I very much focused on just this one box, which is the attention part. In a transformer, what you do is the following. You start with all the memories being just a word, and then you do attention, and then you take the output of attention and you feed it to a neural network, and then you start over again. And you just stack that process. In their paper, they did it 6 times or 12 times. And each time, the memories learn more about their previous words and get better. This diagram has become kind of iconic because it really describes almost the entirety of ChatGPT. So this is the T part. And really what OpenAI's brilliance was they said, why don't we make this 1,000, right? Why don't we make that as big as we can, right? It keeps on getting better. Let's just figure out how the heck we take this diagram and just make it bigger. And I was kind of joking, but I think it was kind of brilliant in some way, just to be that confident that this works. Let's try it. Let's go for it all. Cool. So old-fashioned neural network, attention. Attention deals with the history and the memory. Okay. Other question. Why not X? Why not some other approach? There are thousands of papers with other approaches for this problem. And I often get frustrated because when I look this up online, it'll say, attention is like memory, and memory is important. And that's like an infuriating argument because it's not falsifiable, right? Like other things are like memory, or other things are not like memory. Like why should one work better than the other? And I think what's really key to note is that attention is good, but it also is extremely efficient. And there are mathematical reasons why computing attention works really fast on modern machines. And so I want to go through attention one more time just to convey to you why this is a really nice way of long-term context. So we're going to do the following. We're going to note that, well, we don't actually need to just predict this last word. To compute perplexity, we need every word, right? We want to get our distribution for every word. So all of these words have a query. And we can stack all those queries up in a matrix. And all the keys, well, they're also basically a matrix, right? And all the values are also kind of a matrix. So we think of the shape of these objects. We have basically one query for every position by whatever its hidden size is. And then one key for every position by what its size is, and one value for every position and what its size is. Okay? So if we go through our operations, the first operation is multiplying the queries by the keys and then taking a softmax. So that consists of a matrix multiplication where we're basically getting something back that's going to be the length of the sentence by the distributional property we computed by the length of the sentence. So you get this basically new matrix back here that you then take a softmax of. That gives you the histogram for every position. And then, oops, sorry. Then you can basically matrix multiply the output of that by the values. And then use that to predict the next word. And I think the main thing I want to convey is that our 3 steps correspond to 3 operations we've seen so far. When we say query scores keys, that's a matrix multiplication. Then softmax is applied to that matrix. And then this average weighting is also a matrix multiplication. So mapmul, softmax, mapmul. And this is this formula you've probably seen before. It's like the iconic formula from the Transformers paper. It describes basically the main operation at the center of what they're computing. And it basically describes the little diagrams we've produced so far. And so what they showed in this paper is that while there are many ways to get memory, this is a way to get memory that just happens to basically use just these 2 kind of operations. Now, we have a generative transformer, but I haven't told you yet why the heck that's important, that we've made this mapmuls in this way. So in the next section, I'm going to really dive in to why you can compute this fast on modern hardware, and particularly talk about why these operations are basically efficient to run. Let's see. I think I want to take a break first, though. So I want to make a couple of things clear just from questions. So one thing is, I'm only showing this for one step of attention. So I have the query looks up the key value and then use it again. And that is actually how it was first designed. But one of the key innovations of Transformer and the paper I mentioned was that they do this process multiple times. And what that gets is it starts to look something kind of more like reasoning. So not just look up one word and use it, but kind of multi-hop. You have a query, you use it to get a key value. Then this neural network, instead of predicting the next word, predicts the next query. And then you do it again. And then by the time you've done it 5 times, the query has had the chance to look back at, say, 5 different keys and use them to kind of make its final decision. So I simplified it, but I didn't want to make it too simple. And then that's what I'm showing on this diagram. So when I say 12x here, that means basically the number of hops you do with this process. The final thing I want to note is that the Q, K, and V, they're not parameters, they're activations. So what that means is they're like intermediate values that got computed by the neural network. They're not learned. The learned part is here. This is a standard neural network. So the learned part is there. And this part of the neural network, it's the same neural network that gets applied to each position. So this neural network, it doesn't get to see the whole sentence. It just gets to see each position, compute a new value, and then that gets fed back into the next round of attention. So just going back to our example, so these keys, they all came out of a neural network that was just applied to the words. Then this query looks them up and comes back again to produce the new query. It then goes through the neural network, and then we run this process again. Yeah?
I'm trying to follow. So you're saying, so when we were talking about things earlier, the thing you feed into the neural network would be this 10,000 vector. And so you're saying each key is a 10,000 vector?
Sorry, it's a little more complicated than that. The first layer of the neural network maps from 10,000 down to a hidden dimension. That hidden dimension, let's call that 1,000. So it's much smaller after the first layer. And that's the thing that gets used in this process.
So it's a distillation of the original.
Yeah, it's one way to think about it, so in terminology that's not important for this tutorial, but just to answer this question, the 10,000 vector feels big, but it's sparse, right? It only has 1, 1. The thing you get out is smaller, but dense. So they're roughly comparable sort of things. Okay, great. So let me get back to the kind of key issue we got in here. We want to understand why attention is good. And I made this claim that attention is good because it looks like a matrix multiplication, but I didn't tell you why that's good. So what I want to do in the next section is talk about matrix multiplication. And this is going to be very different than what we've done before. So I want to talk first about why language models suddenly got so much better. And I cannot emphasize enough that this is the answer. That all this other stuff is important and necessary and amazing work and should be super celebrated. But like, it was really essential that the underlying hardware develop. And in some sense, I think of AI as like the application that made sense on GPUs. And GPUs are the thing that is like getting better, right? So like by kind of finding the right thing that ran on this hardware and the hardware getting better, then that's how this came. And like I can make this argument from like a technical point of view, but since we're near the business school, why don't I make it from like a stock price point of view? So like from the point of view of the last couple of years, like it's hard to argue with this graph. This graph looks a lot like the Perplexity graph, but like I would say less important. Other people might say more important. I don't know. I cartoonishly have had this graph in my class lectures since 2020, and never did it occur to me to just buy stock. It was in my lectures. I have proof that I had this in my lectures for many years. It looked like a big graph even then. But anyway, so NVIDIA is a company that makes GPUs. There's like a worldwide shortage of GPUs. NVIDIA is like worth as much as Apple or something. Like it's pretty crazy. What they do is they build hardware that runs the kind of applications like language models. Okay. Now, the move from CPUs to GPUs really fundamentally altered the way we think about these problems. And I'm going to give you an example of just like how it changed the research landscape just to have a different underlying compute. So let's take this example here. So I told you the softmax function was really important. I told you you exponentiate and then you normalize. You normalize by your dictionary. But dictionaries are really big. For every word token in your New Yorker article, you have to take a sum over the entire dictionary, right? That is actually pretty slow. And if you're going to talk about running language models where you're in the billions or trillions, you can't be like having a for loop here to compute this value. So around 2010, if you look back at the papers, you'll see that there's all this super interesting research into approximating softmax. So the thought was like, oh, well, most of the things in this sum are like low values and like it's kind of a expectation in some sense. So like you can approximate it and get close precision, blah, blah, blah. The papers are really fun. But like after that, it's just GPU, right? You just don't care anymore if you have hardware that can compute this really efficiently, right? So everything really changed at this point. And like some things that were hard suddenly became easier. And if you remember, attention had a big fat softmax in it, right? So like we need to be able to take that softmax over all the previous tokens. And so it's really nice that GPU can do this kind of thing efficiently. Okay. Any questions just high level about GPUs? So instead of teaching you how to program for GPUs, what I want to work through is one example. So one of the things that GPUs are extremely good at computing is arbitrary matrix multiplication. Matrix multiplication is essential to computing neural networks. As you saw, it's essential for attention. And I actually think it's really important to understand why that's true. So I'm going to walk through an example programming on a GPU to give you some intuition for why matrix multiply is efficient. And we're not going to see any code, so don't worry about that. I want to kind of just give you mathematical intuition about how GPUs differ as a computing platform than regular computers. Cool? So I find it's really important when I get to this section of my class to make the GPU figure as cute as possible. That's because this portion of the class, like, just for some reason destroys my students. So it's important that it be very cute to make up for that fact so they don't give me a 0 in the course guide. But for you guys, I promise you're smart. You'll get it all right away. So we're using a GPU. A GPU is a parallel computer. It has many what are called threads. The threads run like normal computers, but they run simultaneously. And the way it works is that you literally have to write the same code for all the threads. They're all just running the same code simultaneously. This can be really hard because you can't like put in print statements, right, or breakpoints, because you have thousands of guys all running simultaneously. Now, to bring some order to the chaos, we're going to group the GPU threads into what are called blocks. So this is a block. And the block, this one, is made up of 12 threads. Each of these are running the same code simultaneously. But they have access to this guy here. And this is what we're going to call block memory. So all of those threads can write and read to block memory. And they can do it very fast. So this guy can write something. This guy can read. And they can use that information to do their computation. The blocks are further grouped into what's called a grid. And this grid represents kind of what you're paying for from the GPU. This is all the threads that you have available. All of them are running the same code simultaneously across the GPU. These threads can read and write from what I'm going to call global memory. This one can write to global memory, and this one can read that value. Now, the key rule of GPUs. Global memory is bad. Block memory is good. That's the game. It's a very hard game. But if you can code in such a way that you never read from global memory, only read from block memory, then you can make amazing things run efficiently. Now, you might think, well, this is really easy. I'll just make my block giant. Doesn't work that way. There's a fixed size to how big your block can be, kind of hard-coded in the GPU. You can't make the block infinitely big. It has to be a fixed size. And so you have to kind of solve problems where most of the computation is happening in the block and not in global memory at all. So here's the game. So this is bad. You can't just have each of your threads read and write from global memory. That would be easy. It would work, but it would be slow. Instead, you have to kind of think of it in this two-step process. Stage one is reading from global memory into block memory, but that shrinks things down to these smaller blocks. Then you do all the computation in the block. Maybe you do multiple rounds, and then you write it out again to global. So if you can do this, then it will be fast. Then you can kind of invent new algorithms. Then you can make these run efficiently. Okay. Ready for an example? Any questions about the hierarchy? So what we're going to do first is we're going to compute 3x3 matrix multiplication. Just a reminder, here's how matrix multiplication works. You take a row in B and a column in A. You multiply each of these values by each other, and you sum them up, and you get your output value. The natural thing to do is to just assign one thread to each of these output positions. So computing this and computing this is the same code, right? They're both just multiplying things up and then summing them, but for slightly different positions. That's allowed, but it's exactly the same code. So we should be able to just assign one thread to each of those. But that's bad. That's bad because both of these guys need to do a bunch of reads from global memory, right? So let's count it up. I need to read 1, 2, 3, 4, 5, 6 values from global memory, sum them up, and then write one out. So while I could do that, most of my time and energy and dollars will be spent on global reads. All good? So what do we do instead? So instead, we're going to first read everything we can into block memory. We're going to calculate the results in that block memory, and then we're going to repeat as many times as we need to compute the whole matrix. And here's the kind of key intuition. Do you see these two elements? This one here and this one here. Note that they have different values from B, but the same values from A. So if those values had been in shared memory, I wouldn't need to read them twice. So that kind of overlap is what we're taking advantage of. So this is what it looks like. The first thing we do is we use all of our threads to just read in values from here into here. So the full A into our shared memory, so into our block memory, and the full B into our block memory. That is 2 times 9 reads, or you can think about that as 2 reads per thread. Once it's there, we can then, within the block, calculate each of the output values by simply reading the shared memory, the block memory to compute the output. So these reads are basically free compared to these. And then different threads in the block compute different output values. So all in all, we end up with 2 times 9 reads, or 18, versus 54 from before. We're basically getting a discount because different threads use the same values. So by first reading them in the shared memory, we save having to read them from global memory twice. It feels relatively straightforward, right? It's just a game of figuring out where the reads are. But this is basically it. I mean, this is the trick for GPUs. If you can get this down to as small a number as possible, you can make these be very efficient. OK. Any questions about that? Yeah.
Just curious. So the global memory is bad because of like the physical constraint, or we can intend to do that?
You're asking why it's bad?
Global memory is bad.
Let's think of it as just bad because it's slow.
So it's like the physical constraint, or we intend to do that.
Yeah.
It's like differentiating like to the, say, the local memory.
That's a good question. I'm not a hardware person, so I don't totally know. But because the global memory has to be connected everywhere, right?
Oh,
so you can't make it so fast, whereas the block can be kind of co-located. I don't know. I don't want to say something dumb, but it can be much faster because it only has to serve that very small area. Yeah. Cool. I think this is generally true though in a computer. There's all sorts of different memories, and they're all kind of by by different constraints, some are faster than others. Yeah.
This is different than caching that we have in CPUs, like layered cache, or
It's similar. I mean, this kind of idea of a memory hierarchy is very similar. It's a little bit more explicit in GPU programming, so you're not reliant on the cache. You're explicitly saying I'm using this for this. Yeah. Cool. And then when you code this up, basically what it looks like is you just have two arrays. One is global, and then you have one that's block, and you can decide which one you're using. Cool. Okay, great. Okay. Awesome. So that is the easy case. But in practice, we do not know the size of the matrix we need to multiply. And most of the matrix we multiply are going to be way bigger than our block size. So we have to be more clever. So I think of this algorithm, like if you get this, this is like really, really good. Like this is like, you have much more understanding of how ML works than I think most people who use ML. I think very few people kind of totally grok this algorithm. So we have to deal with a 6x6 matrix, but let's say our blocks can only have 9 threads. We can't do what we did before because we can't load the entire matrix into the block memory, right? It's not going to fit. And if the matrix doesn't fit, then we can't possibly multiply across the rows and the columns. So what we're going to do instead is we're going to read part of the matrix into our block memory, do some computation, write that computation out to our block memory, and then read some more in. And for that to work, we have to basically take advantage of the structure of matrix multiplication. So here's what it looks like. So instead of reading the whole matrix in from global, we're just going to read the top left into here. Instead of reading this whole matrix in, we're just going to read the top left into there. This is 2 times 9 reads, just like we had before. This is a 3x3 block, and this is a 3x3 block. We're going to use these two to compute part of what we need to fill this in. We're going to take advantage of the fact that matrix multiplication is linear, it's additive, so we can do part of this as we go. So once we do this, we then use our threads to fill in each of the different values in this output. We do that by just doing what we did before, multiplying each of these and summing up their values and putting it into block memory. Okay. But this is not the final value of the matrix, because we've only done half a row and half a column. But it is summable with the rest. So once we've done this and filled in each of these values, we then slide over left to right down here and top to bottom up here what we read in. Now we read this into shared memory and this into shared memory. And that, again, is just 2 by 9 reads. But this is the second half of the column we need, and this is the second half of the row we need. So then we do this step again. Now we multiply these up, and we sum it to the previous value. So now we've done 2 big block reads from global memory and 2 calculations of a 3x3 matrix. Once we've done that, we now have everything we need for the top left quarter of the matrix. Since we have everything we need, we can write it out to global memory. So now we have our global memory with this top left part done. So we did a 6x6 matrix with only 2 times as many reads as we did a 3x3 matrix. But what about all of this other part? We haven't touched any of the bottom or the right part of the matrix. But remember, this is just a single block. for the GPU, we have a whole grid. So this block, it calculated the top left of the matrix, and then maybe this one did the right, and this did the bottom right, and this did the bottom left, right? So each of them, since they have their own block memory, can do exactly the same things that we saw. So there were 3 other things happening that we didn't see, but looked exactly the same to compute this, this, and this in the process. Okay, so what did we do? Every one of our threads ran basically the same code. They only did 2 things. They loaded from global to block, and then they multiplied and added within the little block. The 4 blocks we used basically all acted independently of each other. They never had to talk to each other. And the only way that the individual blocks communicated within the block is the fact that they reused similar rows and columns that were in shared memory. So doing this algorithm allows us to compute matrix multiplies really efficiently. It fully takes advantage of the parallelism of these machines, and it ensures that basically we're utilizing this block memory to the kind of maximum extent possible. So this algorithm, when you call it within, say, CUDA code, goes under the name GEM. We focus just on this A-B part, but you can add in some of these other parts as well. And it's a kind of an essential kind of building block for building up these systems. When people assess the quality of a different GPU, they compare how fast it is at computing these gems. And when they think about a model, they think about how many of these and how big they are when you stack them up together. So when we think about a transformer, we can just think about it as a series of these operations. So here's an example. So we saw for attention that you have this calculation there and this out here. Both of those are just kind of gem calculations. Softmax is actually a different operation, but also efficient on GPUs. So we're kind of best taking advantage of the hardware we have available. Here's an example of a graph, I think, put out from an NVIDIA blog post. It talks about 3 different generations of GPUs. So this is A100, this is H100, and this is some extension to H100. What they're comparing on is gems, MLPerf gems, and then this FP16 means that they're doing it with a smaller floating point value. So what's nice about having a smaller floating point value is you can fit more of them in your shared memory. So in modern GPUs, people think very hard about how much storage each of their numbers take up, because as we noted, there's only a limited size here. And if you can fit more in here, then you can make this bigger, right, and compute faster the matrix multiply of the whole thing. So people now are talking about like FP8 or like int8 or like other like kind of smaller formats even to kind of speed this up in practice. Cool. I really hope there isn't like an architecture professor in this audience. I'm really embarrassing myself here with terminology, but I'm giving a try at an ML take on this topic. Cool. So I think that's about all I have to say about GPUs. Any other GPU questions? Yeah.
And I think you said this, but so you don't really have a good idea of like what those matrices look like that are going in?
I know that they're dense. Yeah.
Okay, so they're dense. Yeah. So okay, so you can't do like sneaky things like assume that they're symmetric or make them sparse or something like that.
Really good question. There are some people who have looked into kind of sparsifying matrices or kind of forcing certain types of sparsity on them. One thing that's very tricky is that if you notice these operations, like even if this were sparse, we couldn't really do anything about it, right? Because we're computing it for the whole group simultaneously. So what people often talk about in GPU world is what's called a block sparse matrix. So like, for instance, if we knew that this whole block was all zeros, right, we could just ignore this whole thing. So if you can say like a 16 by 16 block of my matrix is all zeros, then I can really save a lot of time. But just having a couple zeros in random places doesn't really help you. Yeah. Yeah.
You mentioned at the beginning there are very few people that are good at programming with GPUs. I'm curious, like, what would make someone good at programming? You've given us a very simple example.
Yeah. What would make someone good at programming GPUs? I guess being able to ship kind of non-standard things that you can't build in PyTorch. I think very few people tend to do that in research, but I think the ones who can are like highly lauded for that. So there's a couple of good examples of this. There are like, there's a paper called QLoRa that people really like. That's like, you need to do GPU stuff. There's some other stuff in kind of parameter efficient modeling. There's a recent paper I really like called Mamba that does this. Yeah. There's a famous example of actually computing attention more efficiently called flash attention that actually, we could go through the details. You probably know enough now to understand that paper, but it basically makes an argument about computing actually the attention formula more efficiently. So there's one problem, which is that you end up having to store this matrix in memory, in global memory, and that's really slow. So even if you do this matrix multiply fast, you end up having to write that out. So if you can avoid writing that out by doing this all in one operation, that's really good. Yeah, just I'll give a quick plug. If you're interested in GPU programming, I have a series of puzzles online where you can do it in Python. So they're like little puzzles to learn GPU programming. They're called GPU puzzles. I'm not good at naming. Yeah.
So everything that we learned here about GPUs and the way that the block memory works, is that also directly translatable to TPUs? And in practice, are those more used for stuff like this?
Yeah, it's a good question. My understanding is that there is no way for humans who do not work at Google to program for TPUs. So people generally do not write TPU code unless you work at Google. When I talk to people at Google, I get a sense that it looks relatively similar to this. There is a recently released library that looks really cool called Pallas, P-A-L-L-A-S. It's like a general purpose library that targets both TPU and GPU from the Google team. It looks pretty neat. And it has similar principles. Like you have to think about this idea of what is your block memory and what is your global memory. Yeah. So yes, I mean, it's a similar architecture. But there isn't like an equivalent way to just easily code for a TPU. Cool. Great. Let's keep on going. I made you just sit through 20 minutes of me talking about matrix multiply. I think for some people in the audience, you're like, that's kind of boring. I don't care. Why are we so obsessed with speed? Is this just to hit benchmarks, or is there a real reason why it matters how often you load from global memory? And the answer is that there's reasons that language model optimization is intense. That there's like actual tangible benefits to doing this slightly better. And people have been thinking a lot about this recently, like what this means, why we care that it's so fast. So in the next section, I want to talk about that. So I want to talk about why GPU optimization matters by talking about what the point of this all is. So I want to talk about scaling, and the formula we'll talk about is called chinchilla. Okay. So we now have most of what we mean when we talk about GPT. The GPT is a large language model. It stands for Generative Pre-trained Transformer. The generative part was Perplexity. The transformer part was attention. But this pre-trained part, we haven't really talked about so much. So I could talk to you about how training works. It's not that interesting. We basically just try to make Perplexity go down on the training set. We do this by taking the gradient of perplexity, and updating the parameters to try to make it go down. What's a little more interesting to me these days is how much data you train on and how big of a neural network you use. So how big a neural network you use is basically like how much can it learn? How much information can you fit inside this box? It kind of limits how kind of complex functions it could learn of your data, how much memory it could utilize, what sort of behaviors it could learn. The other question is how much training data you give it. So we know that giving the model more training data means its general purpose perplexity goes down. If it's seen lots of examples, it can generalize better and use those to answer other questions. It also just gets more knowledge because it kind of just sees more facts about the world that it can then utilize later on. The models seem like they can do things like memorize documents and stuff like that inside the system. So 2 properties: neural network size, training data. Size, data. They both matter, but it's actually kind of challenging to know what is the next model we should build. This kind of problem comes up everywhere, but it really comes up when you're doing like rocket science or like major foundational decision making, right? Like you have to decide beforehand what these 2 things should be before you spend billions of dollars actually doing it, right? And so scaling is all about how do you estimate these questions, how do you decide what you want in practice. Okay. So here's why this matters. The bigger your neural network is, the more compute you'll use. The more training data you use, the more compute you'll use. But there's a multiplicative factor where if your model is bigger, it's going to be slower per example because you'll have to run more layers of attention. You'll have to basically take more time for each one of those layers. And for the current generation of models, there's an easy heuristic, which is that each data point touches each parameter. So if I send a new word through the model, it basically touches every parameter. And so this scales multiplicatively. That makes sense? So the total amount of compute, which we often call flops, is going to come out as the multiplication of the neural network size and the training data. So here's some examples. So here are 3 famous models that we have data for. So BERT base was released in 2018. It has 109 million parameters. It was trained on 250 billion words. And this is the amount of compute, 1.6 times 10 to the 20th floating point operations. This is GPT-3 from 2020. 175 billion parameters, 300 billion books, 3.1 times 10 to the 23rd flops. Now, I glazed over these numbers for like many years and just didn't care. It's weird that people give it to such precision. If you're interested in this stuff, I really recommend just thinking of it in terms of like Fermi, like sizes. Like this is a really big difference, right? 109 to 175 billion, right? So we're within 2 years, we basically did 3 orders of magnitude of the size of these models, right? Tokens actually are not that different. And then this one gets more tokens and is slightly bigger in this way. So it's worth kind of just getting a sense of what these numbers mean, how many tokens, I don't know, 1 trillion tokens actually is, what the amount of compute actually means to run this model on every one. Cool. One thing that OpenAI observed and wrote about in really interesting detail in this paper called Scaling Laws is that all of these factors help the language model. So if this weren't true, it would be very bad. It would mean we're spending a ton of money and not getting any benefit. And so they show that if you increase compute or parameters or data size, you get these graphs where you get basically decrease in the perplexity proportional to the scaling. What's interesting about these graphs is they're all log-log. So you get this kind of like a linear line on a log-log graph, which kind of indicates that if you really invest a lot in each of these things, you'll see continuing returns on your perplexity. So this is kind of arguing that major investments in either compute, parameters, or data size will lead to proportional gains in your perplexity. And if we take the axiom that perplexity is all that matters, then you get better and better language models. Okay. So the natural conclusion for this, which I really credit OpenAI for just jumping on very early, was just to like, let's make it really big, right? Like if you see these kind of plots and you can get investment, this is the time where you want to build your rocket ship, right? You want to make a kind of concrete targeted investment in one thing, since you're going to kind of predictably get that gain out. Was there a hand? Yeah.
My question is more about like the correlation between the increase in the size of the model and the sample size. To my knowledge, there's no like rigorous statistical methods that can tell us how many training data do we need, but is there like any guideline for additional parameter, how many?
I think we're getting there. So give me a slide or two. Yeah. Any other questions? Yeah.
So every once in a while, you see in the news that some company announces, "Oh, we released this model. It's the pre-trained model is much more smaller than this one."
Yep.
There is another thing behind it that they probably maybe use, I don't know, 10 times more data to gain 10 times safe.
It's a great question. We're going to get there too. Yeah. Yeah. Any questions just about these quantities, what they mean, where you get 1 trillion tokens? Cool. Okay, so, and I think this intuition is right. I really want to convey that, like, let's make them all big is right. The problem is the following. You need to tangibly utilize the budget that you have. So if you have $1 billion and you give it to NVIDIA, they'll give you flops. They'll give you kind of compute, right? And so once you have that compute, you have to decide how you're going to actually allocate it. And the allocation decision really can be abstracted in the limit to this question of, do you want more parameters or do you want more data? Now, this wouldn't be true if every day someone was coming up with a new model that changed this formula. But I think even by 2020, people were like, transformers, perplexity, works, let's go, right? So once you have fixed those variables, it just comes a question of like, how big, how much data? So one method is like you train lots of data and you have a teeny model. The other is like have a really big model and train less data. They both cost the same, right? You're gonna have to pay that amount of compute. So which do you do? So here's an example. We saw this model, PaLM. This was from Google. They trained a very large language model. They went with this strategy. So big robot, little books. Let's look at the picture. Here it is. 540 billion parameters, 700 billion books. Right. That's a particular decision they made to allocate that amount of compute. Is this right? How do we know, right? We're like not in that, it's like not that crazy of space. There's only 2 variables, right? But it's probably extraordinarily nonlinear. Like we don't know if this was the right decision or like what this learned. Okay. So the main formula we're going to look at for this section is a formula that utilizes the power law assumption we saw before to try to extrapolate out the performance of models. The formula is relatively simple for one of these formulas. but it does take a little bit of trickiness to understand. So what we're going to try to do is we're going to try to model the expected perplexity upon completing training. We're going to say that that expected perplexity is simply a function of two things: the amount of parameters and the amount of training data. That value we think is a power law of those two things, which we can write down in this equation here. N and D are inputs. The rest of the values we're going to estimate. This E value represents the best perplexity. Someone asked about that earlier in the talk. That's like, if like this is the ideal perplexity you could ever get from language. So you can't ever do better than that. And then this term kind of represents how far you are to having like the best model, and this term represents how far you are from having like the best data. So the equation looks like this. We're going to have these two values, and then here's N, our model. Here's D, our data. And what we don't know is how much these two terms contribute to the final value. So we need to know the coefficient of our final perplexity that comes from the parameters and the coefficient for our final output that comes from the data. In the paper, they go through various different ways to estimate these two coefficients. Some of them are more kind of theoretical based. Some of them are just running a ton of experiments and drawing curves. What they find from this paper is that under very, very precise assumptions about your model class, your training algorithm, your learning rate, all those kinds of things, like within like the universe that we've converged to that's like very, very narrow, you can make assumptions about what the final perplexity of the model will be. And the assumption is quite nice. It says the coefficient on your model and the coefficient on your data is roughly the same. What this implies is that because we're in this nice world, this equation has a nice answer. You basically remove a degree of freedom and get what's called a compute optimal scaling law, which says if your goal is the best perplexity, you can simply just say the best use of my money is to have a model size that's directly proportional to the data size. This is really cool. I love this paper. They were able to go back and say, we did it wrong, right? They were able to kind of go reassess a bunch of results, and they say, hey, that's a rectangle. It should be a square. Right? Like, we know that this formula says you should be equal scaling, so why did we do it this way? And they did it for everyone. Like, they showed everyone was wrong. It's really cool. Like, just make it a square. You're good. Here's the graph. Here's them. This is from their paper. They say, here's tokens, log scale. Here's parameters, log scale. Everyone else was up here. I don't know what was happening, but I think in 2020, people just like wanted to have the biggest model. There was like some thing where it was like, we need to have the biggest parameters. It's important. We're Microsoft. Ours should be 5 times larger than OpenAI's, right? But what ended up happening was that you ended up wasting compute, right? Like if you want to be on this line, that's the kind of equal scaling line. And that's what they showed. They released a smaller model, trained on more tokens, that did better. And they're just saying, like, as flops get higher, we should like roughly still be on that line, right? And yeah, that these kind of like they were good models. I mean, it's always good. Like both directions are good, right? But if you want to kind of use the compute in the most efficient way, that could be wrong. Cool. And this still is like a really just useful thing. I think when people train open source models, this is a really handy guide. And it would be really nice if people who have lots of money to run lots of experiments would release more of these guides, right? Because they kind of prevent us from going off in weird directions. Cool. Yeah, and I think in some sense this is the punchline. Like the punchline is just do it like this. Yeah, I think it's a rather simple story. It's just from the extrapolation you get that in that regard. Now I don't think you should assume too much about this. Like in the future, people might produce models where the compute doesn't scale like exactly in the same way. Like for instance, there's one model that's gotten popular recently that uses a method called mixture of experts. Doesn't matter what it is, but what's important about mixture of experts is that you don't end up paying one parameter per every token. So it has like a different ratio of things. And so it might lead to a different version of these kind of formulas. Cool. Any more questions about chinchilla? Yeah.
Just a quick question. So the like open source models that give different parameter models, like 7 billion, 70 billion, are those, like, is the data that are trained on the same? And if so, are they like relatively different efficiencies then?
Yeah, it's a really good question. This equation kind of only applies to like one data set. I think for each individual data set, you might get slight permutations of this kind of thing. A lot of open source models are trained on similar data, but maybe not exactly the same. When you start talking about multilingual models or code models, things get a little different. Yeah, so that complicates things a little bit in practice, yeah. Is there a hand here? Were you? Yeah.
Yeah, it's kind of a half-baked question, but something like why, is this a purely empirical insight, or is there like a reason that people think this happens?
I think of it as purely empirical. I've seen papers where people kind of go into the details a little bit more. I think it's beyond me, yeah. But if you just think of it as curve fitting, it's already pretty useful. Yeah.
So there is a cost in acquiring a data set,
Mm-hmm.
cost in scaling the model size because of hardware limits, how big the model can be. So how do you incorporate these costs?
Yeah, I'm extremely fascinated by this question. I think thinking about constrained versions of this optimization problem are really interesting. Let me talk you through one, and then we can talk through some others. So one important caveat is that actually this slide is the opposite of what you were saying, but you were saying is cool too. This cost you pay when you do generation, whereas this is only used at training. So if you're planning on using your model, you might say, these two things are not equal. This would be really nice to reduce, but this we don't really care about. Now you were making the opposite point, which I also think is really good, which might be like, this we can make infinitely big, but this requires getting high quality data that might be expensive, right? So I'm going to talk about this first, but I just wrote a paper about this second. So if you're interested in this topic, it's called Data Constrained Scaling Laws. You can look it up. It goes through that and tries to work out that math. But let's talk about this one, because this one's more famous. So what if I don't really care about this cost? Like, what if I'm Facebook and I'm just a total chaos agent, and I just want to like piss off the other tech companies by releasing a really good model that everyone can run on their MacBook? Go Facebook, I love it. So they're like, we pay this cost. The user pays this cost. So I want to just go this way more because this is less costly to us. So let's just like train it for them. And then everyone can just run our model on their phone or on their glasses or on their computer, right? And so, yeah, so in this case, you're not trying to be compute optimal. You're not trying to minimize the amount you pay. You're trying to kind of do the best as you can to produce a smaller model. And so what you get is you get a model that's like down here. So this is like more tokens than parameters and here. And honestly, this space has become much more interesting than this space. Because like for open source models, people really want, there's seemingly this like lower bound that like people will use 7 billion parameter models and maybe no bigger. Because 7 billion, I think, runs on a like M2 MacBook. So Llama 2 is like here, and I think people think Mistral is like here, that like people are just kind of putting more and more data into models of that size. Cool. Lots of questions, yeah.
I'm just curious. In the training, I think you mentioned this earlier, you said that the training is just using each observation once in the training.
That's right.
Can you just reuse your training? Because you're probably not getting all of the juice out of it.
Yeah. Covered in this paper. Scaling data. Yeah, sorry, I don't have slides for it, but we can talk about it afterwards. The answer is that every time you use a token, you get kind of less juice out of it, and the juice goes down roughly as like exponential decay. And so if you go like 4 times, you're like fine, but if you start going longer than that, you end up paying a lot per perplexity that you go down. Yeah. Without getting new data, exactly. And then you can get new data from some weird sources, like code data helps, seemingly, even if it's not language. And so like sometimes it might be worthwhile to pull in other sources of data. Was there a question there? In the back.
Do you also look at synthetic text generation in that paper?
So I don't believe in synthetic text generation, but I'm fascinated by it. A lot of people are thinking about it right now. A lot of what I've seen that people are calling synthetic text generation looks to me more like having a better model generate your data and then training on it, which is like a good way to transfer information from a big model to a smaller model, which is useful. But I think is somewhat different than this idea that you kind of infinitely produce data. But it's a super hot topic of interest right now, and I'm curious what people will come up with. Yeah?
Are there ways to clean the data before the training to get high quality data?
It's like so important, and people don't study it enough. I think a lot of it is because it's hard to do in a kind of rigorous way. So I think there's a lot of art to it that these companies have these extremely like fancy data cleaning processes. The stuff people have published on is more like deduplicating data or removing data that maybe has bad perplexity from another model, that kind of thing. But I don't think we really understand exactly what kind of good data means besides the one that's like just terrible, right? Like people think Wikipedia is like way better than other data, but it's hard to prove that or say that in a rigorous way. And I'm very worried. I mean, well, not worried. I'm very curious, like what would happen if like OpenAI couldn't train on the New York Times, like what that would mean. Like I bet their model would be way worse because I think New York Times is really valuable data, but I don't know how to quantify that.
Like training over posts on social media, it's different than training on.
Almost certainly, but again, it's hard to. Let me put it this way: this is about formulas. I don't have a formula for that. I don't know what the ratio of like Twitter data is to the New York Times. Yeah. I do feel like we're going to learn because I think it's becoming an important topic, right? Like the New York Times should get paid for the fact that this model is good because it's trained on the New York Times. But like I don't know how much. Like it would be nice if I could quantify. If I could say it was like worth 0.3 perplexity, then you could put a number on that, right? Yeah.
So I know, I mean, it's a race to the perplexity of 1, but what is the realistic gain? I mean, because I cannot make sense of the scale, like 0.1 reduction in perplexity, the cost goes up and up. So it's, at one point, this becomes a menial task of like, we have to spend $2 billion to just increase the perplexity.
Yeah, you're right, but I guess maybe what I'm saying is that Chinchilla tells you that. It tells you the marginal value in dollars, in flops, for equivalent gain in perplexity, right? So like if you think you need this much better to get a new skill, then this formula tells you kind of what the conversion is.
do you expect at some point we run out of tokens, or like I mean, they can listen to us?
Absolutely, yes. I'll also refer to you this paper, which I didn't prepare slides for, but I have a talk about it as well, and yeah, you can look it up. It talks about this question of what you do when you run out of tokens. People think you're going to run out of tokens. It's a little complex. Like if you, let's see, how much time do I have? There's a nice graph about the expected time when we're going to run out of tokens. It's surprisingly soon, but it's a little complicated. Depends on what you count as kind of a high quality token. If it's like the internet, we're kind of getting near the end. If you count social media or like text messages or something, like there is a lot of text being produced, but kind of the core stuff is maybe getting to a point, yeah. Yeah?
Do you expect that sort of ideal ratio of like model parameters to like training data? Do you expect that to extend beyond like transformer architectures? Or do you think that is something specific to you?
So I don't think it's specific to transformers. I think when these models get really large, the majority of the parameters are in just boring old neural network part of the transformer. So like to me, that part feels like it's doing most of the heavy lifting, and it's going to be the same in most models. I mentioned earlier this like mixture of experts model, which kind of has this different property where not all the parameters are used for every token. So if you have that property, then you get kind of different shapes here, because like you have a different ratio if you're not using parameters or being more sparse. Yeah. Okay. Great. So I think at this point we have a really good sense of how this works. It's a big model that is trained on lots of tokens. It's very fast. If we can make it faster, that's really good. If we can get more tokens, that's really good. This all just helps our perplexity. But we still haven't kind of connected any of this to the first thing, which was the skills we observe when this model actually runs in practice. Like I observe that the model seemingly can do math problems. I don't know why, right? And I'm unfortunately not going to be able to give you like a really tight answer because I don't feel super comfortable with any of the answers that I've been told about why this works. So this formula is about this talk's kind of about things we can quantify. So I want to talk a little bit about reasoning and algorithms. And so let's go back to a specific example. So I really like this example just because it's like the minimal thing that seems really hard and I was impressed by when GPT-2 did it right every time. So like GPT-2 shows this result that it can just do this. It can move this word here and it gets it right way better than a lot of models that were trained just to do this task. And I think that was the first time I was like, oh, this is really like something here. Like this is learning this property just from data without any special training to do this. And it does it really well. Okay. So let's talk about a kind of simplified version of this task. This task is called associative memory. The goal of the task is that whenever you see this thing, you need to remember this letter and then spit it out. Okay. So it could be arbitrarily long. You just have to remember whatever was before the greater than sign, and then later on spit out that letter. That's the task. We do it in the simplified form, so we don't have to worry about language. We can just basically work with the data that we have. Okay. So language models can do this. I don't know how. It's beyond me. It's something in training. At some point they can't do this. At some point they can. A lot of people are interested in this now. There's a lot of blog posts about it. I read through a bunch of them. I think they'll crack it, but I'm not convinced yet. And so I don't know. It's a mystery to me. What I want to talk to you instead is about how language models might do this. So the difference is that there's this nice literature that talks about kind of language models as kind of formal systems. And they kind of think about these problems as, in the best case, if a human got to write things down, how might they design a kind of circuit that would do this kind of task? Does that make sense? So we're throwing out training. We're actually going to throw out all probabilistic modeling. We're basically throwing out all the previous parts of the talk. We're just going to say, what's the minimal version of part 2 that could do the kind of associative task we're interested in? Okay. So there's this very nice paper called Thinking Like Transformers. It introduces this language called RASP. I got relatively obsessed with this paper. I think it's like a really fun paper. And what it does is it introduces a little formal language where the formal language can be translated to transformer. Let me try to explain what that means. So it's totally deterministic. It looks like a programming language. No parallelism, no probabilities, no softmax, no anything. Going back to the simple world where we get to use argmax, we get to build a circuit, and it gets to solve the problem for us. And you can think about this as roughly analogous to a finite state automata, if you've seen that before. So you're going to design a little transformer-like circuit to try to solve tasks. Let me make that more tangible. So we're going to code this in Python. We're going to write a little Python program. The Python program is going to translate to transformer. So it literally can output a system that could be run as if it were a transformer and would give you an answer. Now, it's a little hard thinking like a transformer, so we're going to draw some diagrams. And the diagrams work like this. Remember, a transformer has a query, a key, and a value. The first step is that the query and the key intersect, and then the value produces the output. So instead of using matrices for this, we're just going to say we can use any code we want to tell how the query matches a key. And then that's going to produce a matrix. And then from that matrix, we take whatever value associated with whatever things were turned on, and that becomes our output. So it's going to look like a little bit of Python code to match the query and the key, a little bit of Python code to feed in a value, and then together that single matrix will tell us what the output would be. It's one of these things I think you need an example for, so let's see an example. So let's say I wanted to write a RASP program that counted how many previous words were before me. So I just want to count up how many words came before my word. So the first position, it'll be 0, then 1, 2, 3, 4, 5, 6, 7. So we say the query, it should be whatever my index is, and the key should be less than me. So it's saying match positions that have the key index less than the query index. So here are the query indices. Here are the key indices. And the positions that get turned on are the ones where the query index is less than the key index. So this is kind of like debugging our little program. This matrix represents all of the things that were turned on. And then we're going to feed in a value. The value we feed in is 1 at every location. And so we basically sum across to get our final output. So let's take an example. So let's say we're at position 3. We're at position 3. We match these 3, and then we sum across, so that's 3 at the output there. Any questions about the notation? This first part tells us what this matrix should look like, and the second part tells us what we feed into the bottom part. Let's do one more example, and you guys can ask a question. So let's say we wanted to do the following. We had some input, and we wanted to shift everything by 1. So we're going to say, match the key index to the query minus 1, and then feed in whatever the input to our sentence was. So remember, our input was A symbol, B, C, D, E, F symbol. Here's our matrix. It's shifted by 1 because that's what we said here. The query matches the keys, shifted by 1. And then we sum across, taking whichever one had the value for. So the final output is our original string shifted by 1. Yeah?
So summing across, what you're actually getting out is like a vector with some weights on them? Or what do you mean by summing across?
Yeah, so in this example, it's pretty straightforward because the sum is only of one thing, and that thing corresponds to whatever the value was at that column. So, so this is D. We got the D here by, quote, summing across this row, which just meant we took this value out. Let me put it this way. There's no probability here. Everything here is just logic. The way the logic works is that there's no kind of vectors. It's just like we're turning on this column. This column had an E in it, so that becomes our final value.
If you wrote a program which was value tokens, but was the prior key indices thing, what would you get out?
Prior.
Like your first example, it was all ones, and then you conveniently added them all together to get 3.
Yeah, if the value is numeric, then it can sum them. If the value is symbolic, then you can only turn on one thing at a time. Yeah. It can't sum like like A's and B's and stuff. So this is kind of acting like the weighted average, but it's just a kind of simplified version of it. Okay, any other questions about this? It's a little counterintuitive at first. Okay. So let's just look at one more example. So this is an example where we want to find a token that we've used before in the past. So we're going to kind of use these kind of formal operations to try to build up a matrix that spots a token that we've used before. So in particular, we want to find, so that's us here, we're this symbol. We want to find the fact that we've used that symbol before here, right? So we want to find that symbol, and then this tells us that none of these symbols were used before, but this symbol was. So like finding the fact that we've used one of the words before in the past. So we're going to do that with logical operations. So we're going to look for a key that we've used before. We're going to look for a token that we've used before at an indice that came before us. So we're looking for something in the past that we've used before, and we're going to take that indice out. So I think, I think it's, as with all kind of programming paradigms, I don't think you're going to fully grok it just from seeing this. But what I want to mainly convey is that the minimal parts of this language are these little kind of logical formalisms that represent matching keys and queries. Once you have that match, which is this matrix, you can move stuff around in time. So for this kind of problem where we want to move something around in time, we can think about it through kind of learning these little operators. So here's the full program. So this is a program that takes what we did in the last slide and then uses it in the model. And what we're going to see here is the benefit of using multiple layers. So the way the Rasp language works is it automatically separates them into multiple layers if you use the output of the first program. So here we're using find, which was our last slide. So this is find. And then we're going to use it as the input to a second attention layer. So this first one finds that we have used this before at this position. And then the second one uses shift to find something that was one step before and output that. And this gives us a program that outputs whatever was before the greater than symbol. Here's the same program on a bigger input. So we can basically take the same code. It gives us the same way of matching. And we get out basically a different matrix representing a different input of this form. So here it's the letter Q that came before the greater than symbol that gets outputted from the system. Cool. So practically, almost certainly, this is not the way that a transformer would learn this kind of thing, right? Like, if you look inside a transformer, it's crazy town, right? There's stuff all over the place. But here we have these nice, clean, sparse matrices, right? That like simply find something, pull it out, and give it back to you. But it does actually give us a kind of constructive proof. Like if we can code it in this language, then you can literally generate the weights of a transformer that would run this program. So like we have just proven that it is possible for a transformer to find something in the past, use it to generate the next step. And you can prove some like bonkers stuff in this way. Like we have this blog post and we showed that with 6 layers of transformers and like some very kind of hard to write code, you can actually build a full-on adding machine. So here I'm showing 683 plus 345 gives 1028. And I don't need to go through each of these steps, but like here are the matrices. So we're like moving stuff around, we're combining stuff, we're like adding stuff over time, and like you can produce like real programs that do this kind of thing. And so like I don't know how a transformer works, but now I know that you only need 6 layers of a transformer to produce an arbitrarily long adding machine. It's cool. I don't know. I could do that. That's neat. I don't know how useful that is. I certainly wouldn't want to do it this way. But it does kind of give intuition about like what's plausible. Cool. Any questions about this? Yeah.
The question is the value, can it only be the thing that happens in a context? Could it be something that is in my vocabulary, but not necessarily in my context?
In this kind of program, the only thing you have access to is context or constant. So the only thing that can change is the context. But you can also have constants if you want. Yeah.
Yeah, it's just I was thinking about another associated example, like
yeah.
if I type the leader that the president of the United States in 2008 is, right? The model somehow gets some part of the kind of so-called factual knowledge.
That's a really interesting point. I think that you could imagine a version of Rasp that has access to like a database, and that would maybe be equivalent to what you're describing. I haven't seen anything like that that kind of takes into account the fact that there's like knowledge that exists in the actual model itself. Yeah. Yeah.
If you train a code generation model on Rasp, could you build a model that will effectively generate like these different like transformer models?
This is the problem. Like code generation models work like basically on Python and JavaScript because there exists a trillion tokens of Python and JavaScript, right?
Assuming that one day.
So like we don't have this thing yet where we can kind of just give it a new language and like have it just like work in the new language. Like we'd have to sit down and just write a lot of Rasp. And as far as I know, there's like 50 lines of Rasp in the world that exists. Yeah. Cool. I'm running low on time, so why don't I'm just going to go ahead. I only have a couple more slides. Okay. People have done crazy things with this. So this blog post I saw the other day, someone took our code for writing adder in Rasp, and they're like, I'm going to add a backdoor to this code. So they're going to be like, I'm going to have an adding machine that works all the time except for one input. And for that one input, it's going to output get pwned in transformer, right? So this program is like hundreds of lines of code. It's really wild. But they basically just took the adding machine and they're like, how do I like change the weights such that it like has this kind of secret property in it, right? And I think people are really fascinated by this kind of thing right now because like we don't know if we can guarantee that language models work or if they work for all inputs. They do weird things sometimes. But what if like you release a model and you literally backdoor it manually, right? So it like does weird things in a controllable way. So I thought that was a really neat example of how thinking about these sort of constructive problems intersects with the actual use.